Fouché, Kolmogorov complexity and Fourier aspects of Brownian motion.
Thank you. First of all, my thanks to the organizers for the invitation and arranging this very pleasant conference. Well, before I give the underlying history, I just want to introduce two analytical concepts which would, I think, while we are still fresh, it might elucidate the theorem that I want to discuss with you. Firstly, I want to talk about an idea in Fourier analysis. I call it sets of multiplicity. A set of multiplicity is such, it's a subset of the unit interval, say, such that one can find a formal trigonometric series that vanishes outside the set E, but is not identically zero in the sense that not all the coefficients are zero. So a set of multiplicity is such that its complement that there is a trigonometric series that vanishes outside E, but this trigonometric series is not identically zero. Another formulation is that there is a Lebesgue integrable function that converges, for which one has a formal trigonometric series that converges everywhere outside E to F without being its Fourier series. This notion goes back to Riemann. He used it. He worked with the contrapositives, the sets of uniqueness. A set of uniqueness is such that it, if a trigonometric series vanishes everywhere outside the set, the trigonometric series is identically zero in the sense that all the coefficients are zero. Okay. Now this set E alpha is a concrete example of a set of multiplicity, and it was constructed by Bloom in 1998. The contour set, the one that was being discussed this morning, is a set of uniqueness, for example. While this one is one of the few known effective representations of a set which is a set of multiplicity. The construction is an effective construction of the mi's, natural numbers, and then one take the intersection over the union of all the prime numbers between mk and 2mk of all the x, such that its distance from the distance of px to the nearest integer is at most 1 over p1 plus alpha. So what one does, one cuts out varying segments. It is a contour type construction. And he showed then more that E alpha is a set of multiplicity. He showed that the so-called, the Hausdorff dimension of E alpha is the same as the Fourier dimension, and which implies that it is much stronger than, but it implies that it is a set of multiplicity. Okay, most sets of multiplicity are constructed using random sets based on Bernoulli processes, but most frequently the strongest constructions are in terms of Brownian motion. And my aim today is to give another example of a set of multiplicity constructed from Brownian motion and then related to algorithmic randomness. Now, first of all, I just want to make a few remarks on countable dense random sets of reals. Countable dense random sequences are typically studied in statistics. They are statistical ensembles. But sets, from the point of view of randomness, are slightly more complicated. But they arise very naturally in the theory of Brownian motion, as I will discuss today, the construction of non-classical noises. This is fairly recent work. And Fourier analysis, and algorithmically random Brownian motion. And what makes them particularly interesting and challenging is the fact that natural models of countable dense random sets are not Polish spaces. They are singular spaces in the terminology of Kechris, of Borel cardinality F2. But yeah, this, I repeat here what I've just said. What is required is probability theory over orbit spaces under the action of the group S infinity, the symmetry group of a countable set, on the space of all injections of n into the unit interval. And as they are not Polish. But they have an interesting statistical theory. Charlson developed a very powerful approach to random processes over these singular spaces, and he convincingly showed that they manifest in very concrete and interesting statistical properties of countable dense random sets and new aspects of Brownian motion. And these results can be used to construct interesting sets from Brownian motion and its effective algorithmically random version. Okay. We'll look at 0, 1 to the infinity. Just look at the very last line. I think 0, 1 not equal infinity is the space of all of infinite many copies of the unit interval, and then you look at the subspace of it consisting of all the distinct elements. You can think of them as all the injections of the natural numbers into the unit interval. And in that way you can topologize it, and it's a nice Borel space. Now we look at S infinity as the symmetric group of a countable set with a pointwise topology, and then we have a natural action of S infinity on the space of all distinct element sequences. The action is the logical action. It's no fun, it's a technical word when you act on a countable set of objects. And the orbit space under this action is then 0, is then denoted, or is given there with a canonical topology induced by the natural projection. In everyday language, we look at pairwise distinct sequences of elements in the unit interval, countable. And then we identify two such sequences when one is obtained from the other by permuting the indices. And then you can say the orbit of that action is fully given by the underlying set of the sequence. So this is just a way of going from a sequence to a set. Fine. Now, a countable set is then simply just like X there. It's a mapping from some standard Borel space to the orbit space that factors over some y via pi. In other words, it maps a random omega to a random set which is obtained in a measurable way from a sequence. This is what the commutative diagram says. And in the future, I will denote this quotient space by CS01.
So a random sequence of reals?
Yes, in the unit interval.
So independent random?
Yeah. They need not be independent.
What is, you say random sequence, why? What does it
I mean, it's a measurable mapping, Y, from which maps every element in omega to a sequence in such a way that Y is measurable, where O1 has that Borel structure. No, fine.
But, yeah, so Not so. Not every such mapping can be further.
This is really an open question. I can't, even Tittleson said he thinks so, but he can't prove it. So I don't have a counterexample. So this is unfortunate, I hope, but at this stage I have no choice to place the extra requirement, but I don't know an example. This is a nice problem. Although the work is fairly recent, I think. Right. And then one has the idea of statistical similarity. If we have two random sets, probably defined in different probability spaces, we say they are statistically similar if they have the same distribution in the space of sets. Right. And this is a very remarkable concept. Let me just look at one example, the uniform random set. This is the most obvious way. You simply just, your probability distribution is the uniform distribution on each interval, and you choose the sequence independently, right? And then associate it with a random set by identifying via the group action, and that one calls the uniform set. Now, if I place on every, if I make, instead of, still make it independent, but instead of uniform, let us take any probability measure on each unit interval, which is absolutely continuous with respect to the Lebesgue measure. Then we get a new distribution. As sequences, they are totally different, but as sets, they are similar. This is the theorem of Tittleson. I think it's an amazing theorem. The proof is, well, very difficult, 80 pages. But I want now to introduce a very interesting countable dense sets. First, the idea of a local minimizer is something like this. I tried to draw a typical Brownian motion. Imagine this is horrible. It must go like this, of course. It's nowhere differentiable, so you can't draw it. But the idea is a local minimizer in I is the point T where the minimum is attained. It's a theorem that almost surely every unit in any interval has a unique point where the minimum of the Brownian motion is attained. Moreover, if you have any two disjoint intervals, the local minimizers will be the values, the minima, the values assumed will be different. Try to draw that. Well, this is computationally extremely useful because one has at least a canonical, with any I, you can canonically associate a minimizer in the interval. There's just one. And what I was trying to do is, and well, probably did, was show how one can compute the local minimizers relative to the interval for effectively algorithmically random Brownian motion. Okay. Now, I think the climax of Tittleson's book papers is that he showed that the uniform distribution and the set of local minimizers are similar, statistically similar. Now, min is defined on a Wiener space, for example, right? This is your probability space. And U is then defined on, well, unit intervals, infinitely many copies. And they have, as sets, statistically similar properties. Secondly, all Borel properties of countable dense sets has measure either 1 or 0. It's a very strong 0-1 law on the class of countable dense random sets. This makes it a non-Polish space because these measures are not atomic. And if you look what it means to be the 0-1 law, you see it's actually a basic principle in statistics, the Hewitt-Savage theorem. You can also relate it to the Finetti theorem. But it's basic ideas in statistics that it is reflected in at least min as well. So the aim of this project is to find explicit construction of random objects in terms of Kolmogorov complexity via the minimizers. Okay, here's a recent theorem. Okay, I'm still in the random world. Let MK be any random enumeration as a sequence of the local minimizers of a continuous version of Brownian motion. And then we normalize it a bit to, well, not a bit, we want it to be very rapidly decreasing. And then we construct all the sequence of plus or minus 1 times sk's. And the k factorial is inserted to make sure this set E is extremely thin. It must have Hausdorff dimension, otherwise what I'm saying is not going to be true. Now, the sequence sk is then strongly, let's forget about strongly, so just linearly independent over the rationals. It's a subset of a Hamel basis over Q. And E carries a non-zero Schwarz distribution whose Fourier transform vanishes at infinity. I've repeated this. This means exactly, via some standard functional analysis, that E is a set of multiplicity. Right. Again, this means there is a formal trigonometric series with some ck being non-zero, such that the series converges to 0 everywhere outside E. Okay, the proof used strongly techniques of Eve Meyer and Salem, where they proved something similar for independent sequences. And then I invoked the Tittleson theory to show that the statements can be transformed into things which remains invariant under permutations and a few other things, and it worked. Right. Now, what is the link with Kolmogorov complexity? Let us look at the triangle. On the left we have Kp, which is the Martin-Lev random reals relative to the Lebesgue measure. C is the Martin-Lev continuous functions relative to the Wiener measure. Sometimes it's referred to as complex oscillations. I think in honor of the pioneering work of Asarin and Prokofsky, who related what we nowadays call algorithmically random in 1986 already, directly to Kolmogorov complexity itself. And this link, explicit contact between Kolmogorov complexity and algorithmically random Brownian motion is also studied by myself and Jos Hansen and Sabados. And fine, that is what C is. E is a subset of the Baire space, and they are encoded versions of elements. There's just one of elements here, of C. And phi is a canonical recursive isomorphism. Phi is that which is induced by the Levy isomorphism, which was discussed, I think, on Monday. Yeah. And, well, phi I is the natural identity map, in a way. It associates the code for E to the function. And the code is in terms of the value of the function at all the dyadic rationals, which you can simply see placed in a matrix form. Binary codes, and then phi becomes a recursive isomorphism. And I is nowhere continuous, which is also a reflection of a standard observation in statistics. If you work with the continuous stochastic processes, there's an enormous jump in information going from its values at, say, the rationals to itself. It can always wiggle. Because remember, C here has the uniform norm topology, which is a very rigid. But it is a Borel isomorphism. Okay. Yeah. So, using this link, I firstly showed that there is a uniform algorithmic procedure that, given an algorithmically random real alpha, will yield for any closed dyadic interval a sequence of rationals that converge to the unique local minimizer of the complex oscillation. Moreover, all the local minimizers of a complex oscillation are non-computable real numbers. I think they are all random, but can't show that. The rate, you have alpha and you have an interval, and out of that you can systematically, using only initial segments of alpha, you can generate a sequence of rationals. And you can prove, that it converges to the local minimizer. But the proof that it gives me no information at this stage as to the rate of convergence. This prompted George Davey, a colleague of mine, and I, to see whether one cannot find the rate of convergence instead of initial segments of alpha, but at an upper bound for its incompressibility coefficient. And we have shown that the answer is yes, so it is layer-wise computable in the language of Hoyrup and Rojas, for example. But whether the local minimizers can be computed from alpha alone is an open problem, and it is also open whether or not the local minimizers are all random. And I have the conjecture the local minimizers of a complex oscillation are linearly independent over the field of recursive real numbers. And this is literally almost surely true. In the sense that set of complex oscillations for which this statement holds has been a measure 1. But this is an open problem. The linear independence over a field, or even if it is a recursive field, deals with, of course, identity is the problem here. And sometimes I think I have solved it, and then what I can prove, if instead of algorithmically random, if you allow the properties of the Brownian motion to have descriptions which are pi 1 1 light phase, then it will be true. So if you go to hyperarithmetic, then things will work. You need one quantifier over the reals, but I can't prove that it's intrinsically the case. Oh yes, and all the local minimizers can be described by a single sigma 4 light phase sigma 4 0 predicate. I don't know whether this is the best possible. And oops, no. Do I have time? Well, here is another A of boldface A. Think of it as a very thin sequence. For example, you can think of it as all reals of the form plus or minus sums of this form. right? It's very thin. So you look at the continuum of all possible sequences, which series or numbers which can thus represent it. Then, if X is a complex oscillation, algorithmically random Brownian motion, then the image of the set under X will be linearly independent over the field of computable real numbers. And the image will contain no computable numbers. And I think this brings me to the end of the talk. Thank you. Here are some references.
Other questions?
Yes.
So what's classically the distribution of, so first the question about the randomness, is it for the minimizer or the minimum?
Minimizer.
The minimizer. What's classically the distribution? Like an interval, what is
It is a scaled version of the arc sine law.
And it has to be random. Because you said it was layer-wise computable. And so if you have some kind of smooth distribution which is computable, and by randomness preservation, it should be also random for the arc sine law, and that's...
That's a very useful remark, yes, of course. So because I've worked out the distribution, so yes. So this one problem is already solved. They are all random, the local minimum. Thanks.
Any other question? So in this case, it means that the random countable sets are the same as if you take a random sequence of independent chosen real numbers, and you take the set.
And you take the
get
set,
same.
Although they can be totally distinct as sequences, the difference just disappears. So it is a very canonical concept. There is a characterization, I didn't have time, of which measures are similar, or which strongly countable random sets are similar to the obvious one. And what is also interesting is to effectivize that similarity. I mean, you can use a string, a binary string, to develop infinitely many independent copies of them. Just use a bijection between n squared and n. And how to relate it then to the local minimizers of a Brownian motion. I think that I don't think it will be too difficult. I don't know.
Any other question? Okay, so thank you again.